Blah, 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 blah. Blah, blah. Ah!
Okay. So, today's lecture is about motion. And as I mentioned in the first lecture, that's really fundamentally all physics is. It's the study of motion and the application of that to all sorts of different contexts, right? And so basically we're starting at step one, which makes sense because it's essentially data, right? So the first notion to kind of start with is this idea of velocity. And I think everyone's familiar with velocity, so there's not much point in harping on this too much, but the one really important thing to remember is that velocity is different than speed, conceptually speaking, right? In English, those are kind of synonymous words, but in physics, we draw a distinction in order to point out the fact that velocity is speed with direction. Okay, so if I say, the car is moving down the street with a velocity of 50 meters per second, technically that's an incorrect statement, right? It's moving with a speed of 50. It's moving with a speed of 50 meters per second, okay? It's moving with a velocity of 50 meters per second straight north, right? And so it's when I have both a combination of a magnitude, the speed, and the direction that I really have velocity, okay? So technically velocity is both speed and direction, I'm mentioning here. And I think everyone knows, it's pretty simple. The definition of velocity is just change in position over the amount of time it takes to cover that distance, right? So remember that this delta notation is the same thing as the final minus the initial, final minus the initial, right? So I'm going to assume from now on that's well known. So if I've got an object and say it's moving from a position that's, say I've got the origin here, called the origin 0. Let's say it starts and it's 3 meters out, okay, 3 meters out. And I start my little stopwatch. Here's my little stopwatch. Say over a time interval of 5 seconds. It goes from a position 3 meters away from the origin to a position that is 10 meters away, right? So if you're given a word problem that's like that in English, first step is always to translate that English into some sort of data, right? And I know basically I'm going to be using this formula because it's the only one I've introduced you to yet, so that's helpful. If the question is what is the velocity here, right? Then basically I need to know what these four quantities are. The initial or the final x value is this 10, right? It's the final position, so 10. The initial position is this 3, right? 3. So delta x in this case is 10 minus 3 equals 7. 7 what? 7 feet, 7 centimeters, 7 millimeters, 7 light years. What is it? 7 meters, right? So technically it's always got units. I personally am very sloppy when it comes to units, and I get razzed on because of that. But to me, the trick in all these homework problems, the first step is always to convert all of your data, whatever it is, into the standard SI units. So since we're talking about length, we want to be able to convert everything into meters. Well, everything's already given in meters, so I can skip that conversion step. But the advantage to doing that early is that once you do it, you don't have to keep track of the units anymore because they're all standardized SI units. As long as I know what kind of quantity this thing is, it's a distance, then I know it has to be associated with meters, right? So that's kind of how I approach the whole units thing. So I end up being really sloppy when it comes to that. So just bear with me, I guess. So anyway, what we're looking for here to calculate the velocity is a numerator and a denominator, right? So we've got the numerator. What's the denominator? The denominator is the amount of time that passes. Well, that's right here, 5 seconds. So final answer in this simple example is going to be 7 divided by 5, which 1.2, I guess, meters per second, right? The interesting thing about units is you can treat them just like you can variables, right? So the numerator here is meters, the denominator is seconds, and so the result is meters per second. So basically, you can think of the numbers as one piece and the units as a separate piece, but treat them the same, right? So when we talk about more complicated units, we can manipulate those units just as if they were algebraic expressions. So we'll do that all the time. All right, so velocity is 1.2 meters per second. Final answer? No, right? Because I just harped on the fact that velocity is both speed and direction. Technically, what I've calculated is a speed because there's no directionality associated with this. In this case, the direction is to the right, because I'm going from here to here. So that's the direction. So if I wanted to be technically accurate, I would say 1.2 meters per second to the right. And we'll talk about more sophisticated ways to indicate direction, but the answer's always got two pieces. It's got a number with a unit and a direction. That's all I'm trying to get at. Yeah.
Why, if the velocity was negative, what would you have said?
So if these numbers had been reversed or something like that.
That's it, the 1.2 meters per second, it was negative.
Uh-huh. So
when
let's.
you said in the direction is in the right, you can come in all that. If it's negative, 1.2 meters, negative 1.2 meters per second.
So if it's negative, it means in the opposite direction. That's basically what it's the short answer to the question. So if I were to say negative 1.2 meters per second to the right, that would really mean this direction, right? So that would be, it would be equivalent. It's the same thing to say 1.2 meters to the left. Negative 1.2 meters to the right is the same as 1.2 meters to the left. So when we're talking about direction, that positive and negative kind of can either sit here or here, I guess, in a sense, right? And usually what we'll do when we, kind of get more formal is we will, in every problem, either implied or explicitly, we will define the x direction. This is like the x direction. And that becomes positive, right? So that it just becomes the convention that anything, in this case to the right, is positive, anything to the left is going to be negative. So, like I was saying, you could either say to the right or to the left. Well, the truth is, as we move along, we're always going to keep the sign with the number, I guess, I'm getting at. We will always be consistent and say, we're measuring horizontal motion to the right. And it's just the algebra is easier. We can deal with positive and negative numbers easier than dealing with positive and negative directions. A good example of when that happens actually is not so much this, but up and down. Right? Up and down, we can talk about the same kind of things. We can talk about a height, right? So if I've got a ball here, and let's say I'm holding the ball, well, my head's about 2 meters high, right? So if the ball starts at 2 meters from the ground, right? And let's say it falls half the distance to 1 meter high, and there's a proper number for this, but for now, let's just pretend that that happens in 0.5 seconds. So how would I kind of express the same thing? What's the velocity in this problem, right? So I would kind of just I would use the same formula. Velocity is change. In this case, usually you use y to indicate vertical, but it's just a label difference, right? It's still kind of fundamentally the same. So this is y, the final y minus the initial y divided by delta t, right? Sloppy, huh? In this case, the final y is 1. The initial y is 2. So it's y, or 1 minus 2 divided by 0.5. So So in this case, I will get a negative number. So this is going to be -2, I guess, 2 meters per second. And that negative is telling me something, right? It's telling me it's not positive, right? See, I'm measuring from ground, and all of my numbers indicate height. That height is, as the number gets bigger, I'm going higher, higher up, right? So bigger numbers are high. That means we're talking about the positive x direction implied in this problem is up. So this negative is telling me information. It's telling me that the direction of the speed or the velocity is not up but down. Right. So there you go. That was more than I.
So would you say that the velocity was -2 meters per second towards the ground?
That's a good question. The way you would. That's a good question. So the truth is, I don't know what you mean usually. So don't worry about this too much. But I guess technically you'd say -2 meters in the y direction.
Okay.
That's how you would say that. But like I said, it would be equivalent to say 2 meters down. I think if, technically speaking, if you said -2 meters down, that would be technically wrong. Does that make sense?
Yeah.
All right, good. So actually that's a little bit of vector stuff, which we skipped in chapter 1, but the purpose of vectors is to capture this directionality. We've only been talking about things that are moving in one dimension, either horizontally or vertically. We're talking about multi-dimensional things, you know, a projectile moving through space. That's where the math starts to get complicated, and trig really comes into play, but I've tried to table that until the next lecture. So we're just focusing right now on definition of velocity. All right, so that is that. Actually, let me just see if I've got an example. I was not as prepared as I should have been. Let's see. Yeah, this first example is a potential application of this formula. So let's just kind of look at it real quick. So example 1, you've got this 3-toed sloth. It's the slowest moving land mammal. That is incorrect because I have 2 boys. I know. But on the ground, the sloth moves at an average speed of 0.037 meters per second. So that is a speed of 0.037 meters per second. Notice I use the letter V and that kind of makes you think of velocity, but really we're told speed, so we're not really told the direction. There's kind of a convention that, I'll leave that for next week. All right, so there's that, considerably slower than the giant tortoise. So we've got 2 speeds in play here. So let's go ahead and call it this. The tortoise, 0.0676. Okay, so after 12 minutes of walking, how much further would the tortoise have gone relative to the sloth? So we're really being asked about a distance, right? I am told a time interval, it's 12 minutes. Right? And how much further is the question, right? So, you know, when you're looking at these word problems, a lot of people struggle. I always really try and focus on, if you get lost, is where is the question? What is the quantity it's asking you for? In this case, you know, just grammatically tear apart the question and it says how much further, right? So that's what answers the question. I need a further. Further is distance or position, right? So basically I'm looking for some form of x. And now once I kind of write this down, the equation that we've been talking about, this v equals delta x over delta t, kind of jumps out at you, right? Because I've got v's, I've got t's, and I've got an x in play. So all these tell me that that's probably the formula I'm going to use. But I've got two velocities here, which means I'm going to have two applications of this formula. Okay. So let's just do S and T. Simplicity here. So I've got a velocity, I've got the velocity of the sloth, I've got the speed of the sloth, I'm sorry. 12 minutes. So this is a really easy calculation. I don't even need to write down the formula, right? If I tell you how fast something's going, I tell you how long it's going, you just multiply the two numbers, right? But this is telling you the same thing, right? This equation, delta x equals v delta t. So actually, this is the definition, but this form is a little bit easier to use in the problems as we go forward. So I want to write it down this way instead. In this case, the distance the sloth moves, 0.037 times what? The SI unit, yes, you're already jumping ahead of me. So the SI unit for time is seconds. So I don't want this minutes, I want seconds. So how do I convert from minutes to seconds? I multiply by 60, right? But what's the general rule? How are you doing this conversion? Because we may have to do lots of different conversions in lots of different contexts. So I'm going to go a little bit slower. And the way I always remember how to do these conversions is basically you are multiplying by the number 1. You can multiply anything by the number 1, right? And I know that 1 minute is the same as 60 seconds. Okay? So if I were to write something like this, this quantity is 1 because the numerator and the denominator are the same, right? So I've got something over something, but those somethings are the same. So this is actually just 1, so I'm multiplying by 1. The reason I do it this way is because I want to cancel these minutes, right? That's kind of how I think about this, is that I'm treating the units as though they were algebraic expressions. So I cancel the minutes, that's how I know I need to multiply by 60. Like when we talk about converting feet to meters, I can never remember that conversion. I always have to, oh my goodness. Silly thing, but, so short answer here, what's, what? 720, yes. 720. 720 goes here. I always use my phone as my calculator. I have a calculator. What's that number? Doesn't work. 720 times. I got 26.64. So what is this? Meters per second? Kilograms? Meters, right? Because we're talking about a distance. All right, so that's how far the sloth goes. What about the tortoise? So, same trick. Got 54.72 meters in this case, and so clearly it's just subtract the two, and that's the final answer. Right? Final answer is 28.08 meters. Okay, that's how far ahead the tortoise gets in front of the sloth. That wouldn't happen either, right answer? Oh. 28. My one and only soapbox about significant digits. All right, so significant digits. This is 4 significant digits. When I write this down, I imply a certain amount of accuracy by writing that last digit down. But there's no way my answer can be more accurate than the numbers that go into the problem, right? The numbers that go into the problem here have got at most 2 significant digits, right? Which means that my final answer technically should not have more than 2 significant digits. Otherwise, I'm implying something that, is not true. So that's why the final answer is 28, and that's technically more correct than 28.08. Right? So when I'm on the board, I'll probably still try and maintain the significant digits, but sometimes I might get sloppy. So I kind of get sloppy a lot. All right. Okay, so that is velocity, and I think spent too much time talking about the obvious. The next important concept that we'll talk about in chapter 2 is acceleration. Acceleration is easy to define, but surprisingly complicated once we start getting into the problems. So acceleration is change in either speed or direction. You can say that shortly by saying it's change in velocity. So acceleration is change in velocity, kind of the same way velocity is change in position. There's a parallel there, but just remember that acceleration is change in either speed or direction, which implies that even if something is moving in a circle, with uniform circular motion, which we'll talk about in chapter 5, it's moving at the same speed in this circle, that's still technically accelerated motion because the direction is changing, even though the speed is not. Now for chapter 2, we won't really deal with changing direction yet. Okay, we're just kind of taking baby steps. So right now, acceleration is nothing more than change in speed for us. Okay. Oh, sorry. So this is the formula for acceleration. Acceleration is change in velocity over time, which is initial minus final over change in time. Or I can rewrite this in the same way and say v minus v0 equals a times delta t, or v equals v0 plus a delta t, or there's just this standard convention, especially with time, to really just start dropping this delta, because almost every time you're just using a change in time rather than a time interval, rather than the exact moment. Like never do you write 12 midnight Greenwich time, right? It's always 4 seconds later. That's the kind of stuff. So this is actually a very useful form of this. The important thing to know about this is it's only true if acceleration is constant. All right. Now you can imagine all sorts of motion, right? All sorts of wiggly, stop, start kind of motion. And all of that involves some form of acceleration. And to really deal with all the kind of variety of motion really requires some calculus. And even then, you can only do a certain set of problems. There's always many more problems than that can be solved analytically. Hence the computer. The computer comes in handy in dealing with that kind of stuff. So the truth of the matter is, even if you're taking this calculus-based or whatnot, once you were to get into the real world, launching real rockets or dealing with real whatever, you'd just be computer modeling stuff anyway. But it does help to deal with some things analytically, and we're going to do as much as we can. So for us, the formulas or the problems that we deal with are all going to be dealing with constant acceleration. Okay? We're only dealing with problems that involve constant acceleration. If for some reason you're given a problem and it's clear that the acceleration is not constant, then you can't use these formulas. You've got to use something else. Chapter 6, we'll talk about a technique for dealing with those. But for now, the truth of the matter is we're only dealing with constant acceleration. Okay? So, given that, I won't say that again, but just this is going to be our baseline formula for the rest of the lecture, essentially. So, this is telling you how acceleration affects speed. Then the next question is, well, how does acceleration affect position? right? X. So we've got this formula, this formula. We've got this formula now. And I want to get A's and X's together somehow. And this slide here is trying to justify this formula. Okay? And that is the connection between the two, that if an object is under constant acceleration, it's moving faster and faster and faster and faster, or moving slower, 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 the distance it moves is connected to the time interval with a square. This actually is historically significant because Galileo is the one who discovered it. Galileo was early 1600s, I guess. And basically, he is the grandfather of physics, right? And so if Newton is the father, then Galileo is the grandfather of physics. And he's the person who really, in a sense, how do I say it? Created the experimental method. He's the first scientist in the modern sense of the term, I guess is what I'm trying to say, in that he would set hypotheses and then he would set up experiments to test those hypotheses. So his laboratory was not in the mind and logic, but his laboratory was putting balls on tables and watching them roll. And there was always this, one of the key questions of medieval physics was how is acceleration and position related to one another? And Galileo is the one who cracked it. And it's interesting because Galileo was also, there's also a story about how theory is connected to technology, and it goes all the way back even to Galileo's time, because before Galileo's time, there really wasn't a way to accurately measure time itself, right? You need a good watch, a stopwatch, right? And so, all the Swiss watchmakers and stuff were about this same time frame. So in a sense, people weren't able to measure and quantify motion until there was a decent way of measuring time. Galileo happened to be there when it happened to be smart enough and all interested enough, and basically figured this out by watching things fall. He's the guy, the famous story, Leaning Tower of Pisa, right? And drops the two balls off the top. You guys know that story? Blah, blah, blah. Yeah, some of you do, some of you don't. That's fine. So this formula, this connection, it's interesting, I guess, for two reasons. One is because of the squared nature of the formula, and also because of this 1/2. The reason I put this slide together was just to kind of justify in really kind of a cheesy way those two facts. So if you look at this, this is just a multiplication table, right? So I've got the products of the two things here. And if you go down the diagonal of the multiplication table, these are the squares. Right? So I've got 2 squared, 3 squared, 4 squared, 5 squared. Right? So collect all those here. Now take the difference between neighboring squares. You get 3, 5, 7, 9, 11. You ever notice that? That these are all odd numbers in ascending order, right? This is just, 3rd grade math, right? It's like magical. Now if you just do the same thing, what's the difference between the neighbors of the differences? 2, 2, 2, 2, 2. So in a sense, if I were to call this position, the change in position is speed. The change in speed is acceleration. And notice that not only do you get a squared motion associated with constant acceleration, but this factor of 2 is there also. And so those are kind of the really cheeseball way of justifying this formula. This is, there's a more formal way if you'd like to read the algebra.
You may, it's in the book, chapter 2. And I can show you later. But for now, what we want to do is apply this formula in some problems, all right? But before I do that, I want to take one more step. This is assuming we start from rest, okay? So if I take my pen and I let go, the height of the pen is represented by this formula because gravity is a constant accelerated force on the pen, okay? In fact, it's worth pointing out that, oh, sorry, skipped ahead. So that assumes we start from rest. What if we don't? So an example of that is a cannonball. So if I've got a cannonball and I shoot it through the air or straight up, just to make things simple. If I shoot a cannonball straight up in the air, what do you do? Yes, that is the right answer. Run like hell. All right, so that was supposed to be funny. Wasn't that funny? All right, so you shoot a cannonball in the air, and it's got an initial speed associated with it, right? It doesn't follow this formula, but it does follow a closely related formula, and that is this, all right? And so this is a very important formula for us going forward, all right? And I guess what I wanted to point out is it's really a combination of the two formula we've already seen. It's this piece here, which is associated with constant acceleration, and it's this piece here, which is associated with the velocity. So if we've got an initial velocity, the position is the combination of the movement that's associated with the velocity plus the movement that's associated with the acceleration. All right? And you can see that if the initial speed is 0, this whole term disappears, and I just revert back to my kind of original thing. So in all cases, the position is basically a combination of the motion from velocity and the motion from acceleration. Now, if we want to take this one step further, this is off book a little bit. But remember in the first lecture, I was trying to make a point that motion is a combination of both momentum and force, that those two concepts are in constant interplay. This is the piece that's associated with momentum, and this is the piece that's associated with force. Okay? So an object, when it moves, it's going to move by virtue of the fact it has a certain amount of momentum, and it's also going to move because it has a certain force that's being applied to it. It's always a combination of the two. It's intrinsic momentum that it has just because it's moving, and the force that's being applied, which is changing the momentum that's carried by the body. That's just for the fun of it. Pretend I didn't say that, all right? Okay, so one last step, all right? I promise. So we've got this formula, which comes from the definition of velocity. Remember, it's only true if acceleration is constant. But given that, this is from the definition of velocity. This is our formula that I just tried to justify, which is relating acceleration with position. If I combine these, in every different way I can combine them, there's really only 3 different ways you can combine them, I get 3 supplementary equations, all right? So these are just combinations of these 2 kind of primary equations. I end up with 5 main equations. That's the point of this slide, is that every problem from Chapter 2 is going to involve one of these 5 equations, okay? So our first step in solving any one of these problems is to identify which one of these are we going to use. And I'll walk through kind of a way of doing that. But so when I talk about the 5 equations of constant acceleration, this is the slide I kind of have in my mind. 1, 2, 3, 4, 5. So before we go to break, let's go through a couple of problems, and I'll show you what I mean by this, okay? In fact, let me just take a moment and write these on the board for a second. So I've got v equals v0 plus at. Delta x is first one, delta x would be t minus. And even with the x's, I get sloppy. Sometimes drop that little delta. I'm going to be consistent. So these are the 5 equations of constant acceleration. Let's jump to an example, kind of walk through it. Let's do number 3, okay? So number 3, what's the magnitude of the yeah, this will be good enough. Okay, so what's the magnitude of the average acceleration of a skier who, when starting from rest, reaches a speed of blah when going down a slope for probably that should say 4 or 5 seconds. All right. So when I look at this word problem, my first step is to take those words and turn them into data. Okay. So basically, I just sit there and I reread it. I go, what is the magnitude of the average acceleration? Acceleration is A. What is A? I don't know. In fact, it's what I'm being asked for. So I'm going to write it down with a question mark to remind myself that's really the focus of the solution. Okay? So what's the magnitude of the average acceleration who's starting from rest? Now that's not a number, but it's data, because it's telling me the initial speed is 0. All right? So this is what I would call implied data. It's not associated with a number, but it's something to kind of be aware of. Whenever you see the words from rest, it's actually the word rest that is the key. From rest or to rest. That's data that you should write down. So we've got 2 pieces now. Reaches a speed of 8 meters per second. That is the final speed, right? So we call that v without a subscript. And last thing is when going down a slope for 5.0 seconds. That is my t. Okay? There's a part B, but I'm just going to solve part A right now. Okay? So this is where you need to get in all of these Chapter 2 problems. You need to get where there are 4 elements written down. If you don't have 4, you haven't read the problem closely enough, okay? Because there have to be 4 pieces of information in order to, 3 pieces of information and a question in order to solve these problems, okay? So that's step 1. So we're okay on that. Step 2 is, based on this, I should be able to figure out which one of these equations I'm going to use. And the truth is that if you look closely, each one of these equations always involves 4 variables, and they're always a different set of 4 variables. I've got v, v, a, t, no x, right? X, v0, t, a, no v. No v0. No a. No t, okay? So basically, once I've got this written down, it tells me which one of these formulae I have to use. I can only use one because, for example, in this, I don't have an x in the problem anywhere, right? Which means that any equation that involves an x is not going to help me, right? So just by writing that down, I know I'm going to use this first one. All right, then. Let's write it down. And then it's just a matter of putting it together and doing the algebra. It's pretty straightforward from here. So what we got, the v is associated with my 8 meters per second. My initial speed is the 0 plus a, which is what I'm looking for, times 5 seconds. And then I just solve for a, right? In this case, it's easy. 8 divided by 5. 1.6. What are the units here? I didn't discuss this yet. The units are, correct, meters per second squared. And the reason for that is that basically the numerator, remember, is meters per second. The denominator is seconds, right? This is speed a speed over a time interval. So my meters per second divided by seconds can be rewritten as meters per second squared. Does that make sense? Let me be a little bit more explicit here. I've got meters per second squared. All right. So that's the answer to part A. Is it right? Oh, can't believe it. It's right. Let's do part B real quick, and then we'll probably take a break. So part B says, how far does the skier travel in this time? So how far is a distance, right? So distance, that means, in this case, I'm being asked for x equals question mark, okay? So now I collect my data, and there's no point in reading it again because it's sitting over there, right? V0 is 0, V equals 8, T equals 5.0. And now, given this set, only one of these equations is going to work, right? So the quick way is to say, what am I missing? I'm missing an A. I'm missing the A, which means I can't use that. That's the one. This is the only one that doesn't involve an A. So let's write that down. 1/2 8.0 plus 0 20. I did that right. 20 is my final answer. Oh, that's right. And significant digits technically should be just 2, so I should drop that technically. All right, that is it. Are there any questions? Of course there are no questions because it's break time. All right, let's go ahead, take a 10-minute break, I guess. Come back at 7:20 and we'll finish things off. All right, so thank you. What do you think? Does this thing work? Is it on even?
Right. Are we ready? All right, let's begin. Woohoo! Part 2, lecture 2. More fun in physics. All right, we have actually covered, oh, why did I erase those equations? Who let me erase them? We've covered most of the material, actually, from Chapter 2 that we're going to need in order to do this. So I think the rest of this lecture will mostly just be application. So sit back and enjoy. T. Okay, so let's just run down the examples one by one, I think, until we hit the last concept I want to touch on. So number 2. So we've got a VW Beetle, goes from 0 to 60 miles per hour, acceleration 2.35 meters per second squared. Remember, just the units, the SI units for acceleration, meters per second squared. You'll get used to that. Part A, how much time does it take for the Beetle to reach this speed? All right, so the first step in solving all these problems is just to capture all the data. So let's read through the English and see what we can capture. VW Belt goes from 0. That is the initial speed, right? To a final speed of 60 miles per hour. Right? These are not SI units. So we have to convert these. Let's do that. Let's set that aside for a second. So we've got 0 to 60, acceleration, 2.35 meters per second squared. Thank you very much. That is in SI units. I'm not going to have to worry about that one. Part A, how much time? T. That's what I'm asked for. How much time does it take? Okay. So, given that, I'm going to look at these, figure out the formula I use, do the algebra, and be done. But before I can start, I need to convert this to SI units, right? So, does anyone know the conversion factor between miles per hour and meters per second?
I don't know about meters per second, but I know centimeters to inches, and you can do a really long conversion.
Yes. Yes. All right, yes.
Wait, so meters or kilometers?
Meters.
Okay. Then that is 1,609.34, 1 mile per meter.
Okay. So both of you are telling me to do something like, let me write this out a little bit more explicitly. Let's do it in another spot right here. So 60, it's miles per hour, right? So I want to kind of write it as a fraction to help me do this conversion. So you're saying use centimeters to inches, and then I'd have to take inches to feet and take feet to miles. You're telling me to just go straight from miles to meters, which sounds a little bit faster, right? So let's do that. So, can you say the number again?
1609.
No, the conversion factor.
Yeah, 1609.34.
Oh, 16, sorry. 1609.
0.34.
What to what?
Oh,
I mean meters to miles, right?
Yeah, that's meters to miles.
Meters to miles, because meters are smaller than miles, right? Yeah. So I look at this and I go, Dave, right? Why? Because I can't do my cancel thing. That's how I know I got this upside down, right? So I literally do it this way. I'm not pretending. So I always do it like that. So I know I've got it oriented right. So my miles cancel. I got meters on the top. That's halfway there. I want meters per second. So I need to convert the hours now. How many seconds in an hour?
3600.
So 1 hour is associated with 3600 seconds. Right? And I keep writing SEC. Technically, it's just S. I don't know why I do that. And then I get my cancel here. I got meters per second. So this looks right. So it's just a matter of multiplying all those numbers together, and I get. Anyone know what's that said that? Someone say 26.81666667. Huh? By the way, there's an even faster way to do this, right? Because there is just a conversion miles per hour to meters per second. And it's in the front of the book. If anyone has a book, of course I didn't bring a book either. But I know someone who's very smart. His name is Google. And Google tells me there is 0.44704 meters per second in every mile per hour. So if I could have done it this way, 60 mph times, it's 1 mphs times 0.4407 meters per second. I'm not saying one is right or wrong. I'm just giving you options, okay? But if I multiply these out, I should get the same answer, 26 point. You can do centimeters to inches to feet to miles if you want. You should get the same answer, right? All I care is that you get the right answer. I don't care how you get it, unless it's copying from your neighbor. All right, so how do you do it? That's the conversion. Okay, so now we're ready to move on to the next step. What's the equation to use? It's one of these 5. Shortcut is to ask the question, what's missing? It's x. X is missing from my letters, which means I have to use the first one again. So the first one means I've got v equals v0 plus at. This is now the 26.8166666667 equals 0 plus 2.35 times t. Okay? Now at this point, someone should say, what? Stop being an idiot. Don't write so many sixes there, okay? I am trying to make a point though, is that in the intermediate steps of the problem, you always want to keep more digits than you're going to need at the end, okay? Because if I were to snip this down to the two significant digits and write this as 27 right here, what that does is it actually introduces an error that will propagate through my solution. If I keep more digits, and my rule of thumb is you want to keep at least 5 because you're never going to want more significance than 5 digits. You keep 5 digits in this intermediate steps and then round at the very end. You always want to round at the very end. Keep 5, 6 digits here, then you should be fine. Okay? So that's why I'm actually doing this, to make that point. But saying all that, then now it's just easy. I just need to divide and get t equals 26.81. 11.41 seconds, right? So here is where I round and say, you know what? Significant digits tells me the answer actually is just 11 seconds. Okay? Which may or may not be right. Oh, 11.4. What? Dave, bad boy. Why 3? Yes. So I wrote 60. Well, I wrote 60, which was a mistake. Because if you look at the way the problem is written, it actually says 60.0. And that's why they put the 0.0 there. That actually is carrying some information. It's telling us that that measurement of speed is accurate to the 3 digits that's mentioned here, right? That's why they put the 0. Normally you don't need the 0. The reason it's there is to give me that information. And this is also 3 significant digits. So that means I'm allowed to quote 3 significant digits in my final answer. If it had actually been 60 versus 2.35, the smaller significant digits wins, right? Because it can't be more accurate than the least accurate data going in. So I think that's why I put 11, because I made this mistake up here. Okay. All right, part B. A top fuel dragster can go from 0 to 60 in 0.6 seconds. Find the acceleration. Okay, that's kind of a different problem. So, but my 0 and 60 are the, whoa,
Oh.
the cameraman, thank you.
Yeah. It says it's not connected, that your battery's gonna die.
Oh, I was worried about that. Thank you for,
Is this turned on?
probably not.
Technical difficulty. Please stand by. Okay, thank you for telling me that. All right, so this is part B of example number 2. So given these 4 quantities, which is the equation? 1, 2, 3, 4, or 5? Number 1? So number 1 has got the initial, the initial acceleration and time. That's it. So we put it all together. Let me rewrite the formula. 26.81667 equals 0 plus A 0.600. A equals some number, right? Yep. Here, in all of these equations, x stands for distance, basically. Yep. The book will use the word displacement, and technically that's more accurate, but I'm kind of skipping over that distinction for right now. Did I do that right? So 44.694, since we're talking about acceleration, the units are meters per second squared. Go to 3 significant digits to get my 44.7 as my final answer. So that actually worked. Can't believe it. All right, what else? What else? Blah, blah, blah. All right, let's do number 5. This is a little bit more challenging, okay? So, number 5. So in this case, we've got a police car traveling at a velocity of 18 meters due north. Technically correct. We've got both a speed and a direction. When a car zooms by at constant velocity of 42 due north. So they're both going in the same direction. So reaction time, the policeman begins to pursue the speeder at an acceleration of 5 meters per second squared. So the police car is at rest, the speeder zooms by, the cop accelerates up to speed, and so the question is, how long does it take the police car to catch up to the speeder, including the fact that you've got this reaction time where the car zooms by and continues to move on, and then the cop starts to accelerate, right? So we've got kind of this complicated problem, 2 cars, 2 things in motion at the same time. So let's start writing down some data, okay? So police cars traveling at velocity, so that's V. I'm sorry, the police car is not at rest. I said it was at rest, so my bad. Police car is moving. So the initial speed of the police car is 18 meters per second, though. Okay? Car zooms by at a constant velocity of 42. So this is the police car, all right? We've got 2 objects. So up to now, we've only been talking about a thing, one thing, the VW Beetle, or whatever it is that we're talking about. Here we're talking about 2 objects in motion, which means we've got to keep track of the 2 sets of data. There's really 2 pieces, so there's a little exercise in bookkeeping, okay? So we've got the police car, keep track of his data here. The speeder, I'll call him, the speeder, is here. His velocity, 42 meters per second, okay? Now, the other kind of piece of implied data here, which probably you've already noticed, is it says constant velocity, okay? So I'm going to write that down, even though it's not really a formula or even a piece of data, but the velocity is constant, because that means that I don't use these formula, because these formula are for constant acceleration. Okay? So Dave, what is the formula for constant velocity? Hey, I know the answer. Constant velocity, there's only one. And you've already seen it. X equals vt. That is the equation to use when we're talking about something undergoing constant velocity. It's the only option. Okay? So, I already know the equation I'm going to use for the speeder. It's x equals vt, and I haven't even finished reading the problem yet. Okay? So, that's the first sentence of the problem. Second sentence, after a reaction time of blah, so this is time, let's call this reaction time of 0.800 seconds, okay? The policeman begins to pursue the speeder with an acceleration of 5, okay? Including the reaction time, how long does it take for the police car? So how long does it take? How long does it take? That's a time, right? It's kind of a peculiar thing in English. Length implies distance, but how long means time, right? Physics teacher is interested in that. No one else is. How long does it take? All right, look at that mess. What the heck? All right. I look over here and I go, Dave told me I should have 4 quantities. I kind of do, but I've got 2 times. It doesn't, something's funny there. Okay, well, what about over here? Well, Dave said we're going to use this equation. I've only got one thing. What am I going to do? Cry, right? That's what I usually do.
The cop is trying to catch up with the speeder, so wouldn't the velocity of the speeder be the policeman's final speed and velocity?
That is a good guess. It's not true, unfortunately, and the reason it's not true is because he's undergoing constant acceleration, and so he's only going to be at 42 meters per second for just a moment, and then he'll be 43 and 44 and 45. So if we were being asked, so in a sense, he's going to hit 42 meters per second, some distance behind the speeder, and he's going to keep going so he can catch up, because he's got to cover an extra distance. So he actually has to go faster than the speeder, right? So now, of course, he's going to catch up to the speeder, and he's going to hit the brakes, right? So he slows down. So that's kind of what makes the problem unrealistic, because we're assuming he just basically catches up and then, I don't know, opens his door and jumps out or something. I don't know. So, but that's a good thought. But that's why it's not going to work. But you're going down the right track and thinking we need some more information, either on the left or the right side. Yeah.
We use our ET from the right side and one of our constant acceleration formulas in place of X.
Say that again?
We use our ET from the right side in place of X in one of the constant acceleration formulas.
That's a good idea, right? Because, I'm just going to put words in your mouth for a second, because the X on this side is the same as the X on this side, right? Because the distance they go has got to be the same by construction, right? The way the problem is set up. They both ultimately have to go the same distance. They're going to be different speeds, but the distances are the same. So this X equals VT is the same on both sides. I was also going to say that the time interval is the same on both sides as well. So that's one of the tricks when you've got this kind of multiple piece problem, is you're going to have to find a bridge between the two eventually, and that's a perfect one right there. Now, we do have a little bit of a bookkeeping problem because I've got V's flying around and it's going to be easy to mix things up. So before I mesh them all together, let's call the police car number 1 and call the speeder car number 2. All right. So I hope this doesn't get too confusing. So I'm going to call this V2. Does this make sense what I'm doing? All right. And so this is V2. This is X2. It's the distance the speeder goes, and basically what I'm saying is X1 equals X2, kind of in a formula. So the distance the police car goes is the same as the distance the car goes, so that means that this X, if I want to write that here, I can write it like this, equals V2T if I want. Now I know that V, why don't I just write it down? Okay, getting there, closer and closer, right? So what else? So now we've got an X, we've got a T, I think, here. We've got an A and a V0. That's starting to sound a lot like this equation, right? So let's take this information and put it in here. Does that seem reasonable? You're like, I don't know. You're the teacher. Okay. So running out of room a little bit, let's just write it here. So the x involved is 42t. The v0 is 18t plus 1/2 a t squared, right? Now when I put it all together and look at that, I go, hey, it looks like I can find out t, right? It's, what's that called? Quadratic equation, though. Wait a minute, is it? Because I can cancel the t everywhere, and I'm just left with 42 equals 18 plus 1/2 times t. Holy snot. This is great, right? Now before I continue, I've made a mistake, all right? And it's an easy mistake to make, and it's just peculiar, it's just because of this particular problem, all right? And the mistake I'm making is I'm forgetting about the reaction time here, okay? Because the police car's motion is the total t here minus this reaction time. I need to subtract the reaction time because this motion here that I'm describing by this equation only occurs after the reaction time of the police car. Does that make sense? So because we've got reaction time here, it makes the analysis a little bit more complicated. But technically what I need to do is, instead of using t here, I need to use t minus the reaction time. And this has got to be t minus the reaction time. That makes sense because the time that's going in here is the time less reaction time, but the t over here is the total time the speeder is moving in the problem. Yeah. Now, when I write this out, oh, I do have a nasty quadratic equation. But I'm going to have to erase some of this. I need more room. Let's do this. Because there's no way to avoid it. I'm going to have to write it all out. So I've got 42 times t equals 18 times t minus 0.8 plus 1/2, 5. Yikes! Seriously? We're going to solve that? Anyone want to do that? Anyone want to come up here on the board and do it? So I, just give me a second here. If I do that, I'm just going to do it in my head for a second, okay? Do that, I get t equals 11.1 seconds, okay? I just did it in my head.
You just multiply it out and you get like that.
I don't know what you're talking about. Let's move on to the next question. No, I just looked at this answer right here.
That's
So.
what we would have done, right?
But yeah, if I show you the solution, you can see right here, basically, this is the algorithm. So I'm not going to go over it on the board because you can read it on the website. But basically, we've set up the problem here in the same way we've set it up there. It's actually slightly different because of the feedback I got. But essentially, we're going to end up with the same kind of thing where we've got a quadratic equation when we're done. Solve it using the quadratic equation. You get two answers. One of them is going to be negative. And we get this. Do you want me to do it? Or do you want me to do it on the board or no? I don't think you do. I'll say that when you go back and read this, what I am calling t on the board is different than the t I've got here. Essentially, what t represents on the board is the total time, including the reaction time. What I've got here in the problem solution is the time less the reaction time. It's after the reaction. Oh, okay. Yes, thank you. I didn't.
Can we just,
didn't actually.
why don't we just wait then? Can you just wait to do the reaction time at the end instead of having to make it more complicated like that?
Yeah, I mean, that's why I did it this way, I guess. And so, but to kind of rewrite this, I guess, since we're on the subject, basically it's the same logic. It's just instead I would have 42t plus the reaction time here, because the speeder is moving both during the motion of the cup and during the reaction time of the cup, right? Equals 18t plus 1/2 by t squared. These are kind of mathematically identical, but this one you can see the algebra is going to be a lot simpler. So I think it should be that either way will get you the same answer. If I were to just sit there and crank the crank enough. But yeah, so you saw that, and it's there. So I'm going to do it. My phone died.
Oh, no, now it started.
That's what I say to that. All right, so let's move on here. I've got one more thing I want to talk about. And that is the acceleration due to gravity. Okay, so I mentioned earlier that, if you have a pen or whatever and drop it under the influence of gravity, it's going to accelerate. And it is true. It's not obvious, but I'm just asserting that the acceleration due to gravity is constant. And so every free fall problem where you have an object that's moving under the influence of gravity and nothing else, that falls in the category of the constant acceleration problems that we've been talking about today. Okay? And the A that is in all of these equations is 9.8. 9.8 meters per second squared. Okay? I think it's 9.806 meters per second squared, technically, but as I've mentioned many times, I'm sloppy. Just remember the 9.8, okay? 9.8 meters per second. And it's worth emphasizing slightly that it's actually down, right? So typically, positive direction means up in the problems, and so the acceleration due to gravity is technically negative. A is minus 9.8 meters per second. It took me a while to figure out why in the book we write G equals 9.8 meters per second. I would get asked this question all the time. Why doesn't it have a negative sign in front of it if the acceleration due to gravity is down? Well, kind of the short answer is this is just representing the magnitude of the acceleration. It doesn't tell, it's like speed and velocity. This is the magnitude of the acceleration regardless of direction. So whenever I use G, I've got to put the negative sign in there, all right? So whenever you see G, this is kind of the bottom line. Whenever you see the letter G, it's 9.8 meters per second squared. Do not put the minus sign in there, otherwise you'll get things wrong. Another way to say this in symbols is that A is always negative G. That's another way to say that. Okay. All right, so if we have an object, and I guess I wanted to speak for one moment about graphs and charts a little bit here. So this is, the fancy word is this is a space-time diagram. And that's because we've got time going across the chart here, and that's and then going up and down in this case would represent literally up and down. Okay, and so what this chart here represents is the x, which normally means horizontal, I know, but in this case x represents the vertical. It's just an indication, it's one-dimensional. The x is here and the time is here. So what this is saying is that the object, I don't want to use my coffee cup right now. the object at time equals 0 is right here. When I let go, at time 1 second is here, has fallen here, 2 seconds is here, 3 seconds is here, 4 seconds is here, and that's plotted on this chart. And this is, anyone know what the shape is? Parabola, right? Parabola because of the square, right? The square. This is like y equals x squared. That's a parabola shape. So, so not only is it a parabola, it's x equals negative 1/2 g t squared. G is 9.8, half of that is 4.9. So that's why this is negative 4.9 t squared. So this is the formula for any object that's moving, that's being dropped from rest. So if this represents the position, or the height, I guess, and this is time, this chart, what it represents is the speed, or the velocity in this case. So velocity starts out at 0, because when I let go, it's kind of, for 1 millimicrosecond, it's just floating there, right? And then it starts to fall down. It falls down faster and faster and faster and faster. The reason this is a straight line is because the acceleration is constant. Right, so it's constantly increasing at a persistent rate, right? Every second that goes by, another 9.8 meters per second is added to the speed of this object. 9.8, 9.8, 9.8, 9.8 is added every second, every second, every second. So you go from 9.8 to 19.6 to something else, to something else, right? And that's what this chart represents. So the linearity, the fact that this line is the clue that we're talking about constant acceleration. And of course here, if I plot the acceleration, it's just that constant number, negative 9.8. So every kind of motion can, these all represent the same motion, right? It's just 3 different ways of looking at it, or 3 different quantities that we're paying attention to. Yeah?
I thought terminal velocity was 9.8 meters per second.
Terminal velocity is a different thing. So, and it's not necessarily 9.8 meters per second. So terminal velocity is the combination of the acceleration due to gravity and it's the balancing between the acceleration due to gravity and the lift, or the drag, on the object that's falling through the air, right? And so if I were to jump out of an airplane, I would fall at a constant rate, 9.8 meters per second is what I'd be dragged down to the earth at, right? But then I'd be pushed up because the air would be basically supporting me, right? And I would hit a certain, and the amount of lift, in a sense, I'm getting depends on the profile I present to the fluid, the air in this case, right? So if I'm falling, I'm going to hit a terminal velocity that's a certain speed, whatever it is. And I pull my chute, right? And I present a different profile, and my terminal velocity changes because the interplay between the two. So that's why it's good to have a parachute when you're falling out of an airplane, because your terminal velocity is less. But it's interesting you bring that up, because that was going to be my last slide, because I did want to just talk about terminal velocity a little bit. But yeah, in all these problems that deal with constant acceleration, they're all unrealistic. In fact, they're not even close to realistic, because the truth of the matter is there's always air drag. So if we're talking about a real cannonball flying through the air, these equations, the book and I make it sound like this is how you would solve the problem. No, you wouldn't. You cannot ignore the fact that it's being pushed through the air. So it's like, if you're shooting a cannon on the moon, sure, yeah, these equations are going to work. They will work. But you're typically not on the moon, right? You're in the air. So when we, in the lab, actually, I don't know if it's the next lab or the lab after, we'll deal with some projectile motion and stuff. The range that we're talking about is short enough that air drag is not significant enough to really matter. But in a real-life application, you would have to take it into account. And it's shocking how complicated it makes the analysis, actually, just that one little piece, which is really why we constantly ignore it. So, all right. Anything else? I think. Oh yeah, this is just one more thing about looking for implied data. So I mentioned before that the words "from rest" imply velocity the initial velocity is 0. The words free fall are now something that should catch your eye, because free fall implies we're dealing with something involving constant acceleration due to gravity, which means that essentially if I see the words free fall, I can write down a equals negative 9.8 on my little list of things, okay? So I don't need to be told a equals 9.8. The words free fall tell me that. The other thing in terms of implied data that I haven't talked about yet is the words at the top. So the reason that gives us useful information is that if I throw something in the air and I ask how high does this go, right? And so say I'm able to measure how fast I launch it into the air, 2 meters per second or whatever, right? And the question is, how high does this calculator get when I throw it in the air at 2 meters per second, right? Well, I go, okay, 2 meters per second, that's the initial speed. I know it's a free fall problem, so I've got the acceleration equals 9.8. I'm asked for a distance, the height, basically. That's really close. I need a fourth piece of information to solve the problem. And the fourth piece of information is implied in the question. Because when I say at the top, what happens at the top? Yes, for just the micromillisecond up at the top, that thing stops, right? And then it starts to fall again. So technically, what I have in that case is, so to use literally the problem I just set up, the initial velocity is 2 meters per second. Acceleration is negative 9.8 meters per second squared. The height, which I'm still going to call x, get used to it, is what I'm asking for. And what I'm saying now is the implied data when I talk about the top of the trajectory is the final velocity in this problem, even though obviously it's not the final velocity, it goes up and comes down. But in the context of the problem, when I'm asking about this distance, I'm asking from this release point to the top, what's the speed at the top? That's the 0 I'm talking about, right? It's meters per second, 0 meters per second. So now I've got a problem that I can solve using the techniques we've already talked about, right? And so in this case, I look and I say, which equation do I use? And it's number 5, right? I've got final, initial, I've got acceleration and distance, and I can solve this problem, right? So those 3 things, when we get to chapter 3, there'll be a couple more we'll add to the list of implied pieces of data, but those 3 things are to watch out for in the problems that you'll be looking at tonight. Yeah, I'm going to skip that, kind of talked about that already. And here's the terminal velocity slide I was going to mention. So, in general, terminal velocity is proportional to your speed. I guess that's why I wrote this here. And there are 2 different air drag is a complicated physics problem because it involves turbulence, and turbulence has kind of got this random quality to it. And so there's actually it's actually the only unsolved classical physics problem that exists is when dealing with modeling turbulence. There is a prize that exists, I think it's called the Millennium Prize, for anyone who can come up with the equations for turbulence, which would be useful in the airline industry and car industry and all that kind of stuff, right? So if you're interested in, earning $1 million or something, you can figure it out, but it might take you a while. But probably the simplest approach is that in general we know it's connected to velocity, and it's a good rule of thumb that if the speed is slow, the air drag involved is proportional to the velocity, period. If the object is large or the motion is fast, it's going to be proportional to the velocity squared. In either case, speed is the key quantity that defines how much back acceleration we get from terminal velocity. And this is why I was saying, so you can see that your profile is going to determine which one of these categories you fall into. and then also the kind of the speed at which you go down. So you go down faster and faster and faster due to gravity, but that also implies that your air drag is becoming larger and larger and larger, and eventually they balance, right? And that's when you've hit terminal velocity, is when essentially this becomes 9.8 meters per second up, right? So the question is, what V is going to make this 9.8 meters per second up? And that's how you figure out what terminal velocity actually is. And that changes the character of these diagrams in kind of an interesting way. You can see that, still you kind of get this almost parabola shape, although technically what this is, it's a hyperbola. And this, the speed here kind of levels out. This is graphically the terminal velocity. And the acceleration starts out at 9.8 meters per second and eventually hits 0, because once you hit terminal velocity, you're falling at constant speed, right? And so if you're falling at constant speed, your speed's not changing. By definition, no change means the acceleration is 0. So that is the last piece of the lecture, but let me go over a couple more examples and then we'll go home, okay? I'm going to do probably 6, 7, 8. We can just knock these out, because they'll start to feel familiar after a while, hopefully. All right, so number 6, dynamite blast. The aquarium launches a chunk of rock straight upward. 2 seconds later, it's rising at a speed of 15 meters per second, assuming air resistance has no effect on the rock. Assuming air, it always does, but we pretend it doesn't. Calculate the speed at launch and 5 seconds after launch. I'm going to skip that one and save it for last, all right? Because it's not that hard, but let's do 7. Hot air balloons. No, let's do number 8. All right, we'll do them backward. Number 8. So, from her bedroom window, a girl drops a water-filled balloon to the ground, 6 meters below. Okay, that's an X. And by that I mean a distance. X is 6 meters. If the balloon is released from rest, you said that's a thing. So, from rest, from initial rest, 0 meters per second. How long is it in the air? How long is actually asking about time. Okay, so, come on! I need one more thing. What is it? Yes, acceleration. So either you just remember it because we're talking about something falling under the reaction of gravity, or you can stop yourself and say, okay, the only 2 options are V or A, right? Those are the only 2 that are left. So that might help trigger, it's A. I know what A is. A is the acceleration due to gravity. So. All right, I'm going to put this together and solve it, right? So, I look at my file, and well, looks like number 2 is up. Number 2, x equals v0t plus 1/2 at squared. X in this case is 6, v0 is 0, t is what I'm looking for. That's what I get when I put it all together, right? Fortunately, that all kind of cancels for me. I get 6 equals negative 4.9 t squared, and I get 6 divided by 4.9, I get negative 1.2248 equals t squared. Take the square root, right? Right, because it's a square root of a negative number. What the heck happened? I thought I knew how to do it. Oh man, so many people. Go ahead.
The acceleration is positive because I think the balance is the balance being released from the rest, so it's removed.
So the acceleration represents how much the speed is changing. falling down. So because it's falling down, right, it's a water balloon. So she's holding a water balloon and she lets go. The object's going to fall down. It's being pulled down. And that downness is what we mean by the negative 9.8 meters per second squared. So it should be negative 9.8. Were you going to say that? You can do that, yes, and sometimes that'll work, and sometimes it won't. There is a reason to do it, though, in this case, and I guess that's what I'm looking for, if anyone can see it. I haven't really explained it, so
Wouldn't it be a distance because it's going down?
that's it, yes, that's at least what I'm thinking, is that this x represents the distance it moves in the time that it moves, right? It's going from up high to down low. So technically, this should be -6 to indicate both that it's falling down and it's moving down, right? So if I'm putting negative here, I kind of have to put the negative here also in order to be consistent. So maybe that's what you were thinking, that inconsistency was going on here. And so this negative sign here is why the book makes a distinction between distance and displacement. The difference between distance and displacement is the same as the difference between speed and velocity. It's an exact parallel. So speed is the magnitude of the velocity, in the same way distance is the magnitude of the displacement. So if I were to speak a little bit more technically, more accurately here, I'd say the distance the water balloon falls is 6 meters. The displacement is -6 meters. And that's kind of, in English, one way to express the distinction we're talking about here. So that negative now shows up down here, which shows up down here, which flips that sign, and now I can actually take the square root, right? So I guess the one thing I want to emphasize in these chapter 2 problems at least, and really in every problem that we do here in physics, the signs should always lead you in the right direction. So you shouldn't have to just randomly drop a sign. If you have to randomly drop a sign, that usually means somewhere back here you made a mistake. I will admit that I sometimes can't figure out where that sign is going sometimes, so I'm not saying that it's always obvious. But in every case, the math should lead you in the right direction. So if you are getting like a negative sign here, you really should step back and say, and look at the logic, because it might be telling you something is significantly wrong. In this case, it was just easy. We just dropped the negative. But so we get an answer of 1.1065 seconds.
If I was driving a car, negative acceleration.
Okay.
What would you register? If you have negative acceleration.
What would register?
If I'm driving a car,
Yeah.
what is negative acceleration when I'm driving a car? Is it velocity or?
It's a good question. So negative acceleration, one way to say it is that negative acceleration opposes the motion of the object. Sorry. No, that's not right. Deceleration always opposes the motion of the object. So there's a difference, I guess, between deceleration and negative acceleration. Negative acceleration implies a direction. So when I say positive acceleration or negative acceleration, I mean positive or negative relative to the positive direction, the x direction. And so in this case, this is negative because I've already established positive is up. Positive is always up. So this acceleration is negative because the speed is increasing down. Right? It's going faster and faster. So in that sense, it's accelerating, but it's going faster and faster downward. So it's negative.
The reason I asked,
But in a car, if you're moving, say you're moving north, okay? If you're moving north, and if, for sake of argument, we establish your motion is positive, right? The negative acceleration is going to be slowing down, hitting the brakes, right? If you're moving south, though, negative acceleration could mean acceleration in the southerly direction. Right? That's kind of the problem. You can, you know.
Define as positive, right?
Yeah. So it kind of depends on your convention, I guess is what I'm getting at. So you have to, before you even start the problem, you have to agree what is positive mean, right? So that's why I'm kind of hedging so much, is because, go ahead.
I got confused because if you have the x coordinate, say you draw a graph, you
Yeah.
have the x and the y,
Yeah.
your initial is from 0,
Yeah.
and you throw something upwards.
Yeah.
I only see it descending, I don't see negative.
Yeah.
Because it's not going back to 0.
So let me draw what you're saying. So you're saying draw a graph like this, and you have an object, and it's going upward.
Yeah.
Okay.
So if I'm standing right, yeah, the initial should be
Here?
0 right there.
Okay.
I'm standing there and I toss a ball up.
Yeah.
And I know that when it comes down, it's not going to pass that 0, it's going to hit the ground. So while coming down, I don't see negative, I only see decreasing.
Okay. So this is the ground.
Yeah.
So this is ground. Yeah. So the object will go up, and then it will come down
That's right.
and hit
I
here.
see decreasing,
Yeah.
I see negative.
Okay. So this is the negative space, negative area, negative position. How do I say it? Right. Negative position, and this is the positive position. Right. That's all. That's true. But what I'm saying is there's a directionality difference, right? So when I say which direction is it moving, it's either moving up or it's moving down, right? And those are two different things. Now I've got another question. Which of these is positive, right? And in this case, I'm saying positive up is moving upward, maybe is a better way to say it, and negative is moving downward. So even if I'm up here, because I'm moving downward, that's the negative direction. So in this case, the velocity is negative.
I think that's how you're framing the problem.
Exactly. So I set that up at the beginning. And so, you know, if every problem were super explicit, it would start out by saying, assume the positive x direction represents positive velocity, right? But it's not going to say that every time. So you just have to understand that generally, negative is downward and positive is upward, right?
That's in both distance and acceleration, we assume.
Yeah. And so if that convention is ever violated, we'll have to tell you that, because you can't assume that that's the case. Good question. Thank you for clarifying that. Anything else? All right. So let's do, let's see what we got here. Let's do number 7. This has got kind of the same trick in it. I actually forgot that trick was in number 8 as well, but we'll see this again here. So in problem number 7, you got a hot air balloon rising upward with a constant speed of 2.5 meters per second squared. Here's the balloon, thing, blah, blah, blah. It's moving upward at constant speed, or constant velocity. It says constant velocity equals 2.50 meters per second. Hey, constant velocity means I get to use this equation, right? Almost. So I have to keep reading. So that's the hot air balloon. When the balloon is 4.00 meters above the ground, so let's draw that here. So we're talking about this gap is 3 meters. The balloon is accidentally dropped the compass over the side of the balloon. So here's the compass. Right? The compass! Spring! So the question is, how much time elapses before the compass hits the ground. So this is true for the balloon, because the balloon is moving with constant velocity, right? We're not asked about the balloon. We're asked about the compass, which is why I drew it in red, right? The compass is in free fall, which means A is negative 9.8 meters per second squared. It's not constant velocity. So this is a little bit of a tricky question because it looks like I'm going to use this equation because those words are in the problem, but actually I don't, all right? But nonetheless, it's still pretty straightforward. What I do here in this case is I'm basically use this as the initial velocity of the compass, right? Because the compass is moving with the balloon and the balloon is being pulled upward, that is essentially the speed at which the compass is moving when the balloon is lets go, right? So the initial velocity of the compass is upward plus, because that's what we're told, right? It's rising upward, so I should have put a plus there to remind myself. So the initial velocity is upward. In a sense, the compass follows the balloon a little bit upward, and then truly starts to fall downward, right? That's the motion of the compass. I know the acceleration. I know this distance now, which is negative 3.0, and I'm asked for time, right? Yeah. And so, lo and behold, I do. I have my four quantities. So, given those four quantities, equation number 2 jumps out. I've got negative. I've got this. I've got negative 3. 2.5 plus t equals, oh, sorry. Right, and so now factor t, that is a quadratic equation, truly and honestly, and I'm not going to do it in front of you. Solution is right here, if you want to write it all down. Let's just double check though. I've got a negative 3. Yeah, that's, so I've written down on the board up to this part, and so then the rest is just out of that. Alright. And what about number 6, the one I was so afraid of at the beginning? Made my knees shatter. Well, let's look at it for a few minutes. Alright, number 6. Dynamite launches deployed, launches attempted launch straight upward. Chunk of rock. Straight upward, right? And 2 seconds later, its velocity is, or its speed, 15 meters per second. Okay. Assuming no air resistance, assuming air resistance has no effect on the rock, which the reason those words are there is because that allows me, technically speaking, to treat this as a free fall problem, okay, which means this, A equals negative 9.8 meters per second, isn't it right? Part A, calculated speed at launch. That's the initial speed, right? And lo and behold, bam, we're there. We've got our four quantities. The equation that pops up in this case is number 4. Sorry, there's no x. Which, number 1, thank you. Number 1. So v equals v0 plus at. guess we'll do this. 9.8 times 2. Did I do this right? I get 34.6 meters per second. That's the right answer. That's 37. All right, got lucky. That's part A. Part B. What is it? What is the 5 seconds after launch? Assuming no air resistance is no frequent launch affecting the rocket. Calculated speed 5 seconds after launch. That's going to be math. Calculated speed. So it's still essentially the same problem, except t is now 5 seconds, right? Final speed is what I'm looking for is 7.98 meters per second. What do I put here? Again, there are two options really. It's either the initial speed or distance. I look at that and I go, I'm not even close to a distance anywhere in that problem, so it's probably initial velocity is this quantity. What is the initial velocity here? Hey, wasn't that what I was just asked in part A? Yes, it was. So you take that and put it here, right? So, and then you kind of just do the same old thing. It's actually the same formula. There is another way to approach the problem. However, this is very straightforward and simple, so this is probably what I recommend. But there is one downside to doing it this way, and it's one thing I try to avoid in multiple part problems, is that I try and avoid using the answer from part A in the solution of part B, because if I happen to make a mistake here, I'm just going to carry the mistake into part B. There is a way to solve part B without even looking at part A, but that's if you say to yourself, what I'm told is that 2 seconds into the flight, I know the speed. I'm being asked 5 seconds later, or I'm being asked 5 seconds, which is 3 seconds later, right? So in a way, I guess what I'm saying is you could then solve the problem with t set to be the 3 seconds after the 2 seconds, right? And in that case, then kind of what these symbols mean changed slightly. The initial speed for that 3 second duration is actually the 15 seconds that I'm quoting the problem, right? So if you're not following it right, but I just want to kind of make this for a record. The initial speed, or the final speed is what I'm looking for in part B, right? There we go. Yeah. And then the acceleration being 1.8. So if you're going to do it this way, and do it this way, obviously you should get the right answer, or the same answer. But this approach avoids compounding errors potentially. So, you know, I think it's the right choice.
Yeah, I was going to ask, the first answer is because the figures tell you that it's 35.
Yeah.
And did that carry error over it?
Yes, it would. So that's a very good point. But you do want to keep, you would treat, for the purpose of quoting the answer to part A, you give some digits, but for the purpose of using it in part B, you have to treat this as an intermediate calculation. So you would want to keep 5 digits or whatever. But then, you know, if you're thinking about the quiz, you're thinking, you know, how's Dave going to treat this kind of stuff? You know, if it comes down to little things like that, I look for understanding, right? If I can see that you understand the concept, that goes a long way. So I do give a lot of partial credit. If I can see that it's just because you chopped off and carried a significant digit with you or something, I'm usually pretty liberal about that. So just focus on understanding kind of the concepts and the ways to solve the problems. So I'm kind of done. Any questions? All right.